Ever watched a soccer ball make that perfect curve through the air and wondered, how does that even work? Or how a planet stays locked in its orbit? Well, these are all examples of what we call motion in a plane. And today, we're going to pull back the curtain and unlock the secrets behind it all. I promise, by the end of this, you'll see how this complex-looking topic is actually made of really simple, easy-to-get pieces. Let's dive in.
So let's start with that curving soccer ball. It's the perfect way to think about this because it's moving forward and upward at the exact same time. It's moving in two directions at once. So how on earth do you describe its entire path with just numbers? Well, that's the big challenge we're going to solve right now.
You know, motion in a straight line is pretty simple, right? We just say positive for forward, negative for backward. We've all got that down. But when you try to describe that graceful arc of the soccer ball, well, a simple plus or minus sign just doesn't cut it. We need a more powerful tool. And that tool, my friends, is called a vector.
I want you to think of vectors as the official language of 2D motion. Seriously, once you learn how to speak it, you can describe the path of absolutely anything, from a kicked ball all the way to a planet in orbit. So let's get you fluent in the basics of this new language.
Okay, rule number one of this new language is knowing the difference between a scalar and a vector. A scalar is just a number, it's a magnitude. So if I say my speed is 60 kilometers per hour, that's a scalar. But a vector has both a magnitude and a direction. So if I say my velocity is 60 kilometers per hour heading north, now that's a vector. See? It gives you the complete story.
So just burn this into your brain. A vector is like a 2-for-1 deal. You always get two critical pieces of information wrapped up together. How much and which way. And it's this two-part nature that makes vectors so incredibly powerful for describing motion in a plane. And then there's this little guy, the unit vector. Think of it like a pure direction signpost. Its size, its magnitude, is always just 1, so its only job in life is to point the way. And to show it's a unit vector, we put this little cap over the letter. Fun fact, in Hindi, they call it a topi, which literally means hat. So yeah, it's a tiny direction hat for your numbers.
Okay, so we know what vectors are. Great. But now for the important part. How do we actually use them? Think of this next section as the user manual. There are really two main skills you've got to master. Adding vectors together, and then, you guessed it, splitting them apart. Now, adding vectors isn't like adding 2 plus 2. You can't just add the numbers, because the direction matters a lot. I mean, if you walk 5 meters east and then you walk 5 meters north, you're not 10 meters away from where you started, are you? So, how do we figure out exactly where you end up?
We use something called the triangle law, and it's actually a really simple visual trick. All you do is line up your vectors one after the other, head to tail. The final sum, which we call the resultant, is basically the shortcut from your absolute starting point to your absolute ending point. But, and this is the key part, remember the little twist at the end. The resultant vector points in the opposite direction of the flow to close the triangle.
Now, I know what you're thinking. That formula looks a little intense. But trust me, it's just a superpowered version of the Pythagorean theorem. You know how Pythagoras only works for perfect right angles? Well, this formula works for any angle. That little extra bit, the 2AB cos theta part, that's the secret sauce. It's the magic ingredient that takes care of the angle between your vectors, making this thing work every single time. All right, let's do a quick check. Looking at that formula right there on your screen, when do you think the resultant vector r is going to be at its absolute biggest, its maximum value? Hint, take a close look at that cosine part. What do you think?
You got it. It's when the angle is 0. That means the vectors are pointing in the exact same direction. They're helping each other out completely. Cosine of 0 is 1, which is the highest value cosine can be, so you're just adding their magnitude straight up. Perfect teamwork.
So we've got adding down. But what about the opposite? What if we have one single vector and we need to break it apart into its fundamental directions, like its north-south and east-west parts? Well, that's where components come into play.
The fancy term for this is resolving a vector, but here's a really cool way to picture it. Imagine your vector is a stick, and you shine a super bright light from directly above it. The shadow it casts on the flat ground, the x-axis, that's your x component. Now shine a light from the side. The shadow it casts on the wall, the y-axis, that's your y component. Simple, right?
And of course, we have formulas to calculate those shadows precisely. Here's a little trick to remember them forever. The component that is touching the angle, the one right next to it, always gets the cosine. The component that's away from the angle, on the opposite side, gets the sine.
It's a handy shortcut that'll save you a lot of headaches, trust me.
All right, we've learned the language, we know what vectors are, we know how to add them, and we know how to split them apart. Now it's time for the big payoff. Let's see how these new tools finally let us solve that problem of the curving soccer ball.
And here it is. This is the big secret, the beautiful, simple truth that vectors show us. That complicated-looking arc of a projectile, it isn't one big, complex motion. No way. It's actually two incredibly simple, one-dimensional motions that are happening independently at the exact same time. This idea is the absolute key.
See, by resolving the initial velocity into its x and y shadows, we can look at them separately. And look what happens. The horizontal motion is just an object moving at a steady speed. That's it. And the vertical motion? It's just an object being thrown up and then pulled down by gravity. We know how to solve those. Vectors let us treat them as two separate, easy problems instead of one hard one.
So that's the whole magic trick. Vectors are basically a cheat code for physics. They let you take an intimidating two-dimensional problem, break it down into two simple one-dimensional problems that, guess what, you already know how to solve. It's a total game changer.
So now you have the key. You've unlocked motion in a plane. But I want you to think bigger. What other complex movements in the real world can you now understand with this power? A boat crossing a flowing river? The moon orbiting the Earth? The possibilities are literally endless. Thanks for joining me.